Good evening. I'm an educator from Kepler Educations, and this is our third video of the POTD series. So, without wasting time, let us start with the POTD that has been provided in GFC today. So, the POTD that has been provided in GFC today is median in a row-wise sorted matrix. Now, this is a hard question, and the explanation is quite difficult, and it will be advisable for whoever is hearing this video or watching this video to pay attention. So, it says that we will be given an n cross m matrix where n is odd and m is odd and the matrix is row wise sorted. We have to return the median of this particular matrix. First and foremost, what is a median? Median is middle value of numbers arranged in ascending order. That is, let's say if the numbers are 1, 2, 3, 4, 5. Then the median value is 3 because it is in the middle. There are 2 elements to the left, 2 elements to the right of this median value. Left number of elements to the left of this median value and number of elements to the right of this median value must be equal. Now this is the case only when the number of elements is odd. When the number of elements is even, then you will have two values 1, 2, 3, 4, 5, 6. Two values correspond to which the left and right will have equal number of elements. So if you consider something in between, let's say value x which is in between, and let's say this x is 3 plus 4 by 2, 7 by 2, 3. So here there are three values, here there are three values, and they are exactly equal to each other. So this is a median. Now, one important fact is that the n and m of this particular matrix, n and n are odd. This means n cross n, m is also odd. Why? Because n is odd, m is odd, and when you do 2n plus 1 into 2m plus 1, the answer comes out to be something like 4k plus 1. So which is odd. So the total number of elements. So total number of elements is odd. Therefore, there is only one median value. This is important. Now, what can be the brute force solution? Let's say the matrix is 1, 3, 5, 2, 6, 9, 3, 6, 9. 1, 3, 5, 2, 6, 9, 3, 6, 9. What can be the brute force value? You write them all down in a linear fashion. Obviously, you can understand that this thing is not sorted. So you have to sort them. 1, 2, 3, 3, 5, 6, 6, 9. 2, 3, 3, 6, 6, 9, 9. So there are two nines. So you see from here the median value is 5. So how much time does it take? It takes, first you are traversing n cross m. Then what you are doing a sorting. This is the time complexity that you are using. Obviously, if n and m are same, the time complexity will be n square plus n square log of n square, which is in the order of n square. This is not acceptable. Space complexity is 1, so you have to optimize it. Let us come to the optimal solution. Now you see for a fact that the entire matrix is row wise sorted. Since sorting is there, it indicates that there might be application of binary search. Now, see, let us take the matrix to be let us assume the matrix is 1, 3, 5, 2, 6, 9, 3, 6, 9. 1, 3, 5, 2, 6, 9, 3, 6, 9. So the question is to find out the median values. Now you can also understand easily that the largest number in this matrix is 9 and the smallest number in this matrix is 1. So therefore the median will always lie between 1 and 9. That is final. So we have to find out a number between 1 and 9. So that will be the median, that is, which will have equal number of elements to the left and equal number of elements to the right. Now let's say find a number x which has equal number of elements to the left and equal number of elements to the right. Then this will be your median. And how to do it? You see, first you start searching. Okay. So before starting on how to do it, Think carefully about something that I'm going to tell you. You see, for 1, how many numbers in this array are less than equal to 1? There is only one number. For 2, how many numbers in this array are less than equal to 2? I am counting all the numbers. Okay, this particular limit. I am counting all the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright. So there is one number in the matrix which is less than equal to 1. There are two numbers in the matrix which are less than equal to 2. There are four numbers in the matrix which is less than equal to 3. There are four numbers in the matrix which are less than equal to 4. There are five numbers in the matrix 1, 2, 3, 3, 5 which are less than equal to 5. There are seven numbers in the matrix which are less than equal to 6. 1, 2, 3, 4, 5, 6, 7. There are seven numbers in the matrix less than equal to 7, seven numbers less than equal to 8, and sorry, nine numbers in this matrix which are less than equal to 9. Now you see, when you write this entire matrix in a, let's say, in a list, in a sorted list, where first there is 1 and at the end there is 9. You see, if you consider 3, then if the 3 is here, then there are 4 numbers less than equal to 3, and thus there are, so 9 minus 4, 5 numbers less than equal, which is greater than 3, less than equal 3. So you see, the left and right hand side are not equal, so this cannot be the median. Forget it. Now you see, if don't forget it now, if if three cannot be the median, obviously you can understand that whatever is less than three, let's say 2, cannot be the median, because if there are four numbers less than equal to 3, there is bound to be some number which is less than 4, which is less than equal to 2, and more than 5 numbers that is greater than 2. So effectively, the left and right parts cannot be equal. So there is no point considering them. The left hand portion. So if 3 cannot be the median, then the entire left part cannot be the median. You have to focus on this sub part. So this is the condition of binary search that you are going to use. The left portion will be eliminated and the right portion will be taken from. So in the right portion, you come to, okay, so 3 0 1 2 3 0 1 2, earlier it was 2. So now the low will be 3, and 0 1 2 3 4 5 6 7 8. Now it is 8. So 8 plus 3 by 2, 11 by 2, 5. So now the median will be at 5 here, mean. See. So 7, so 6. So let's say 6 is here. So till 6, including 6, there are 7 numbers. And 9 minus 7, there are 2 numbers. This cannot be the median. This cannot be the median. But this has a tendency that it will provide the median on going left. That is, between low and mid, the median exists. So we will try to go as left as possible. We will try to go as left as possible to the median x, such that it will have more than 4 elements to the left. Why more than 4 elements to the left? So if it is the median, okay, if let's say total number is 9 and you're required in the end, okay, so total number is 9. So for the median x, there must be 4 numbers on the left and 4 numbers on the right. So consider the left part. So let's say for this 4, or let's say for this 3, can this 3 be the median? No, of course not. They're not equal. Now can this 5 be the median? Can this 5 be the median? For this 5, there are 5 elements to the left of 5, 5 elements to the left of 5, and 4 elements to the left of right of 4. Now 5 elements less than equal to x, yeah, and 4 elements greater than x. So you see, since let's count for 5 and let's count for 4. Let's take numbers 5 and 4. This is the most critical part of this algorithm. For 4, there are 4 elements less than equal to 4, and there are 5 elements greater than 4. Now which one will you consider? You see, you want more than 4. You want more than 4. Why do you want more than 4? Because for the median, the left part will contain 4 elements without the median. So including the median, the left part will contain something more than 4. I am repeating this once again. So for the median x, on the left part you want 4 elements, excluding the median. On the left part you want 4 elements, excluding the median. So can 4 be the answer? No, because on the left part of 4, there are 4 elements, including the median, because of this reciprocal. So you have to exclude the median. But for 5, there are 5 elements to the left of 5, including the median. 5 elements less than 5. So there are greater than 4 elements, including the median. greater than 4 elements including the median to the left of 5. So 5 has a chance to be the median. I will go through it once. See, for 4, there are 4. So what do you want for x? For an element x, you want 4 elements to the left of x excluding the median x. So you want more than 4 elements to the left of x including the x. X will have 4 elements to the left of x include x excluding x. So x will have more than 4 elements to the left of x including x. So here 4 has 4 elements to the left of 4 including the 4. This cannot be the median. But for 5 there are more than 4 elements to the left of 5 including the 5. So there are more than 4 elements. More than 4 elements. Therefore this can be a median. Therefore this can be a median. So this particular thing is very important. Finding out how many elements which is less than equal to x, less than equal to 4, less than equal to 6, which exists in this particular matrix. So this we will see how to find number of elements in the matrix less than equal to x. Before considering this, let us continue with, let us write the pseudocode of this particular binary search. So you see, whenever you find something with more than 4 elements to the left of, let's say x, let's say left of y, then y can be an answer, and you have to search to the left of y. You have to search to the left of y. Why? Because there can be less than y element. Oh, sorry, there can be an element value z which is less than y, but still it has more than 4 elements to the left of z. So this makes z more ideal candidate for the median. And by going this, you will reach the median element, which will have the minimum positive, which will have that particular number of elements to the left of the median, including the median, which is greater than, the number of elements to the left, excluding the median. This 4. It has 4 elements to the left, including the 4. So the immediate next value 5 should be the median. So for reaching this value 5, when you reach this value 5 by going through, by moving backward from, let's say, y, which is, let's say, 7, you find out a number which is the last possible in the array, greater than 4 elements existing to the left, including this particular element 5. So this has to be the median, because anything before this will have, including the element exactly 4 elements. Sorry, exactly, yeah, 4 elements, n by 2, total number by 2. So this is something that we do not want, because this cannot be the median. This cannot be the median. I hope this is clear. Now let us write a binary search for this particular approach. So the low, we will first find out the low. Let's find out the low first. So let's say the low is error of 0, 0. And let's say the low is, yeah, and high is error of 0 and minus 1. So to calculate the low, you can do like this. For int I equals 0, I less than n, I plus plus, low equals minimum of low comma error of I comma 0. High will be, this you can start from 1 to save time even more. Max of I comma error of I comma n minus 1. This completes your minimum maximum. So your low and high are calculated. So you will now come with a binary search. While low is less than equal to high in mid. I am doing low plus high by 2 because the constants are quite less. There is no chance of overflowing. Let us say there are count number of elements in the array which is smaller than equal to mid. Not matrix. I named it as ARR. Sorry. So you see, you have to find out the you have to find out the middle element. So the middle element will have, okay, first the required number of elements. The required number of elements to the left of the array will be total number of elements. Total number of elements is always odd. So total number of element is 9. So 9 by 2 equals 4. So you will find out that you need 4 elements to the left of the median. Without the median, excluding the median, 4 elements to the left of median, 4 elements to the right of median. And the median itself will be a single element. Total 9 elements. So if this median, if count is less than equal to required, if count is less than equal to required, that means number of elements including this particular net is 4 or less than 4. If it is less than 4, definitely it's not a median. You have to increment it. If it is equal to 4, so the number of elements to the left of 4, including 4, is 4. Sorry, left of x, left of mid, including mid, is your required number of elements. But you need something. You need something. You do not need the number of, you need exactly one more than the mid. In this situation, you need exactly one more than the mid. The greater number than the mid, which is present in the matrix, obviously. Not exactly one more, you can do 2 more, you can 3 more, but what is present? The immediate next number that is present in the matrix, not this one. So this cannot be the median. So because it's a 4, it's a 5, it is the median. So this is what it is coming out to be. So this will have, without this number, without this particular 4, if there are required number, this will be required minus 1 number, which breaks the condition. And required plus number on the right hand side. But for 5, it will be required number on the left, required number on the right. So if count is never required, so this will not work. Low equals anything less than that will not work. You have to go high, mid plus 1. And if it is not, then you have to find out the last number which satisfies this condition of greater than, less than equal to the number of elements to the left, less than equal to, sorry, the number of elements to the left, including the median, will be equal to, will be same as that of required. Number of elements to the left, including the median, will be equal to required. So this can be an answer. First, let us initialize this answer variable. Answer equals your mid. Mid is possible. Mid is a possible answer, and you have to decrement. If it is possible, say 12 is possible. 12 is a possible median. You have to find out. You have to go near, because if you move above 12, this breaks the condition. But 12 is already saved here. You start seeing those numbers which are less than 12. Let's say 11 or 10. Say going down. And after the end of this while loop, we will return answer. How to find out the number of elements in this particular matrix smaller than equal to mid? Let's say the matrix is 1, 1, 3, 5, 2, 6, 9, 3, 6, 9. Let us say you have to find a number of elements smaller than x. Let's say you have to find a number of elements smaller than 5. So what will you do? You can either count all the elements, but that will give you an n×n complexity. You can reduce it. You can definitely reduce it. You start from the first row, because only rows are sorted. You start from the first row, you do a binary search and find out the first element in this particular matrix which is greater than 5. You see the first element which is greater than 5 in this particular row does not exist, or you can say hypothetically exists as an index 3. So there are 3 elements which are greater than 5. We go to the next row. You see the first element which is greater than 5 is 2 at index 2. Sorry, at index 1. So there is one element which is greater than 5. In the third row, you see at index 1, the first element exists. At index 1, the first element exists which is greater than 5. So there is one element which is greater than less than 5. So the number of elements which are less than equal to 5 is 3 plus 1 plus 1, 5 elements. 5 elements in this matrix which are less than equal to 5. So you have to go through each and every row. Let us say you have to go through each and every row. So let us say that, okay, this condition is known as upper bound. This condition is known as upper bound. Upper bound returns the first index in a row, sorted row, that has value more than x. This can be done using binary search. Very easy binary search. Let us write a condition of upper bound first. The first element in an array that is greater than x. The first element in the array that is greater than x. So what will it be? You're given an array, you're given an element. So low equals 0, high equals error dot size minus 1. Also, you take an answer variable and to initialize the answer with not high. If you initialize the answer with high, then for this particular row, the answer will come out to be 2. The answer is not 2. You will find out why. If you write on the binary search, you will find out why. But the answer is not 2. The answer is not. The answer is 3. So for case in which the binary search doesn't really find anything out, in which cases like the high goes, sorry, in those cases where while doing the binary search, you see that the low goes after, I mean high remains where it is, high remains where it is, and low moves, low moves, low moves, low moves, and one time low comes after high, and the high just stays static. In that situation, it is in a situation when this is the situation when if x is greater than error above, error dot size, error of n, m minus 1. X is greater than error of n minus 1. This is the condition. In the case of when x, the provided x is higher than the last value of this element, then this thing, this high remains static and the low goes beyond high. In that situation, if you keep the answer as error of the answer equal to high, this means that the high position doesn't really change. So high position continues to remain as it was 2, but your answer was supposed to be 3. So when you return this high, when you will return this high, or when you will return this answer, it will be returned as 2 and not as 3. So you have to keep answer equals. You cannot keep answer equals high. You have to keep answer as error dot size minus 1. Sorry, error dot size. You start your binary search while low is less than equal to high. So whenever you see something which is greater than, okay. So first we will take mid, low plus high by 2. So if your mid, if error of mid, let's say it is greater than x, because you want the first number which is greater than x. You want the first number which is greater than x. So you will say answer equals mid, the first number which is greater than x. You will say answer equals mid, and you will now, you've got the number which is greater than x. Let's say you've got 3 and this is x. So now you will start looking for x. This is x and you want this particular number, which is, let's say if x is 5, this is 6, and let's say you've got 9. So you will look in this direction, not this direction. So high will decrease. So what? And if this condition doesn't satisfy, then low equals mid plus 1. That is, you are still on this part, on this side, still in this side. Here the mid has come. To reach this particular number, you have to eliminate. You have to, let's say 5. You want to reach this number, and you are at mid here. You have to eliminate the entire section and move low beyond mid. So low is mid plus 1. At the end, your answer is stored in the ANS variable. Return answer. Now for each and every row, in the array, in the matrix, 1 3 9 2 6 9 3 6 9 1 3 6. For each and every row in this array, what you will do? 1 3 5 6. Yeah. You will find out the first number which is greater than x. So here the first number which is greater than x lies at index 3. So the number of numbers which is less than equal to x. The number of numbers which is less than equal to x is 3. For this row, the first number greater than x is at index y. So the number of numbers less than equal to 5 is 1. In this row, the first number greater than x is 1. At the either index 1. The number of numbers which is less than equal to x is 1. So for each row you will do, and you will add them up. So there are 5 numbers in this array which are less than equal to 5. So your actual your actual find smaller equal, this this function will be, you take matrix first and you take x. You go for int I equals 0, I less than n, I plus plus. You initialize the counter variable int count equals 0, count equals count plus upper bound mat of I, comma upper bound mat of I comma x. Write in a good format. So you will return count. This completes the code. Before going to the editor, let me just find out the time and space complexity. You see, this upper bound for each and every row takes a time of log m and space of 1. For each and every row n, this particular upper bound is being called. So this function takes a time complexity of O of n into O of log m, and space complexity is 1. And this particular find smaller this thing was used in this particular, in the main question, in the main code. So in the main code, you are moving between low and high. And from the question, you can see the minimum possible value can be 1, and the maximum possible value can be 2000. So assuming that 2000 is the maximum possible value in the question that we are getting, the overall time complexity will become O of 2000 into, for each of that you are calling each and every one of these 2000 entries. Very sorry. O of log of 2000. So let us consider 10 to the power 4. Though there are three zeros, let us consider maximum possible 10 to the power 4. Log of 10 to the power 4, and for each and every one of them, you are calling the find smaller. For each and every mid that you're calculating, you're trying to find out how many numbers in the array are less than equal to mid. So you're finding you are counting find smaller equals for each and every number. So that was taking a time of n log m. So O of n log m. This is your overall time complexity. The space complexity is O of 1. Now let us move on to the code. You see the exact same upper bound code has been written here. The smaller equal function has the exact same name that I was using, and this is the main code. First you take the n and m, low and high. You find out the lowest value in the matrix, you find out the highest value in the matrix. Let us suppose you have a variable, you are making an answer variable, you are initializing an answer variable that you will find. There is no need for this minus 1. The minus 1 is only there because, well, 9 by 2 equals 4 as well as 8 by 2 equals 4. So this is of nothing significant. You can even omit this particular one if you want to. I just keep it because this looks good rather than 9 by 2. You can omit this particular one. If you can omit this without any problem at all. If in fact omitting it would make even much more sense. So while low is less than equal to high, you find out the mid. You have the entire search space of answers. You have the entire search space of answers from 1 to 9. You're finding out mid in there. You're trying to see whether mid can be a median or not. If it cannot, move up. If it can, consider it as a mid. This might be a median. So put in the answer and move left and see if there can be other. If there can be some other number which is a median. So if count is it is the find smaller equal function. So if it is less than equal to required, I've told you this many times throughout this video. If count is less than equal to required, so if on the left hand side of mid there are required number of elements including the mid, then you will ignore it. Why? Because you do not want, you want required number of elements to the left excluding the mid. That is the mid. Required number of elements to the left, required number of elements to the right, excluding the mid. But if the mid falls either part of that number, if it's a part of the required number required, then you will not consider it. So low equals mid plus 1. Else it can be a median, answer equals mid, we reduce the search space, return answer. Now find smaller equal for each and every row. You're finding the maximum element in index of the maximum of the element. Sorry, index of the element which is greater than x. So if the index of the element is greater than x is 3, first element, index of the first element greater than 3. If this index is coming to be 3, then that means 9. There are 3 elements on the left which are less than equal to 3. Less than equal to x. There are 3 elements which are less than equal to x. So you're returning count after calculating this for each and every row, and the upper bound function is a simple upper bound function that we had covered. So you're starting from low is 0, high is error size minus 1, the smallest and largest index of the array, and answer is equal to error size when the high remains static and a low moves beyond high. And in a situation like that, when the x that you are trying to see is more than error size minus 1, more than the maximum element in the array, so in that case, this high, sorry, so in that case, this binary search will be over when low goes beyond high, and the answer this particular block will never execute because the error mid will always be less than x. So your answer will be my error. If you make answer equal to high, then and if this block doesn't execute, then your answer will be equal to high when you return it. So you have to consider this possibility and make sure that the first element in a situation like that, the first element is always the number of elements in the array, which is error size. So all the elements are less than equal to x. So low is less than equal to high. You find out a mid. You see if the mid is greater than x, then this might be answer. Take it, reduce the search space, because obviously if you find out something which is more than x, you have to find out more number which is less than this particular number but more than x. So you reduce the search space. And if you find a number which is less than x, this is not. I mean, this is not the first element which is greater than equal to x, greater than x. So you have to go to the right in the search space, and at the end you return answer. So this is the overall time complexity, the overall algorithm. The time complexity of this algorithm, as I have discussed, is O of what was n log m into n log m times log of 10 to the power 4 at max, and the space complexity is O of 1. I will attach this code as before in this particular notebook for easy for getting this code as and when required. It's a big code after all. As before, as I said, okay, this doesn't look good. Make it no doesn't good, not at all good. I have to find some bright color. Better hopefully. Yeah, better. So this entire notebook for easy availability will be present in the web in the library section, resources library in technical term endpoint of library endpoint in, or you can find it from the navbar. You can find this library from the navbar itself. In the navbar it is provided. Resources section inside a community group of https // kepler22b.vercel.app. This link shall be provided in the description of this video. I hope there is nothing more to this problem. There is nothing more to this problem, obviously, but I hope none of you have any doubts or difficulties regarding this particular problem. This is a very hard problem. Oh, I haven't done and submitted it. Sorry. I'll run and submit it once. I'll run and submit. See, we submitted. So this marks the end of today's video.